It's now my pleasure to invite Jean-Marc Denis to speak to us. Jean-Marc is the Chief Strategy Officer of SiPearl. I like to say SiPearl because it sounds more French.
You won't.
But you will tell us how to pronounce it. And this is this interesting new company that's in place to manufacture the European processor. And you're going to tell us a few things which are interesting, I think, about that and how it presents real opportunities for co-design as we move into this exascale era. So you've got 25 minutes. You have 20 minutes and then there'll be plenty of discussion, I anticipate. So I'll let you know when you have 5 minutes to go.
Okay, so thank you all. Thank you, Peter, for the introduction. So about how to pronounce. SiPearl stands for silicon pearl, from the black pearl, Arabian pirate, the pirate. So it really comes from this. There is an anecdote about it. So the French people used to say SiPearl because it looks very British and in the US. And in UK and in the US, they say SiPearl because it looks very French. So the way you want, honestly, as long as you remember the name, it's fine. So SiPearl is a company, as you have explained, that design and manufacture. We are a fabless company and we don't have a fab. A CPU, a general purpose processor, that is 100% developed in Europe. This is totally new HPC segment. We start with HPC segment, which is a big challenge. It's like climbing on the top of Everest. If you have ever visited the Alps before, something like that. So it's very, very challenging. So I guess that most of you don't know the company or what we do, who we are. So let me make a very short introduction, very, very short. So it's a company that we have created. I'm one of the founder of the company in June 29. And it's coming from the European Processor Initiative that I created, I initiated when I was at Ethos, which was before Bull. I'm the one who created the HPC business at Bull back in 2004. It's not from yesterday. So the CEO is Philippe Noton. He's a driver in the car, and my role in the company is to be the GPS in the car. So Philippe relies a lot on me, only for finding the right direction for the future. So today we have 4 design centers in France, 2 around Paris. Not in Paris, it's inside the city because it's far too expensive. But on the west and south of Paris, 1 in the region of Nice, Sophie Antipolis, and 1 in Grenoble. In France, this is the hotspot for the semiconductor industry. We have 1 design center in Duisburg, Germany, close to Düsseldorf, and 1 in Spain at Barcelona, because it's one of the technopoles in Spain. And we anticipate to open new design centers, all R&D centers in Europe, and eventually also UK. Which is part of Europe in many aspects this year or the year or the next year. We have veterans of the semiconductor and HPC industry, like those STMicro, Marvell, Nokia, well, you can see it. So what we design is processors, no accelerators. We have absolutely no ambition to design accelerators, just make CPUs based on ARM instruction set for the first generations. And very specifically, it is based on the ARM Neoverse V1 core, which is by chance for us the core that is the AWS Graviton3 processor. So when you work on AWS Graviton3 based instance, work on the same core as my CPU. It's not the same processor. There are many differences, but at least the core is identical. So today we are 110 people, and we have new people onboarding almost every day. From week to week, we have 4 to 6 more people coming aboard. So our ambition is to be about 200 people by the end of the year. If we are lucky and if we execute well, 1,000 people by 2025. As I mentioned, we have locations, European places. One remark about our resources, I mean compute resources. They are all located in Europe, all located in France, in the region of France, the capital city for Champagne and region, because we don't want to go to cloud operators, French, European, or US. We want to control our data. So we don't go, and we will never go to cloud operators. For us, it's very constraining, not a real cost, but at least we have full control about what we are doing. And it's crucial for having a complete security. So this year, next year, we will expand around Europe. We will also have very likely a subsidiary in Taiwan because we manufacture at TSMC. So we must, and it's a must have, we must have a location with people in Taiwan to interact and to interface with TSMC. The process we are going to use is 6 nanometers for our processor. So our vision and strategy for the years to come is quite simple. We start with HPC, with CPUs for high-end supercomputers. So what we target is the top of the top 500. Then we will downscale the technology to data center and cloud computing. So there are many actions going on with cloud operators and server designers for data center. And then through time, not before 27, we will also start addressing the infrastructure edge segment because the volume and the demand is just massive. So we are going to move from the most demanding technology with very limited volume of production to massive volume production on the less demanding technology segment, but very competitive. So this is the only way for us in order we can sustain our growth on the reinvestment on R&D. So in terms of overall roadmap on the articulation of the product we are designing with the European, with the Euro HPC strategy. So I will not elaborate on Euro HPC. You know, we have discussed about it earlier this morning or maybe later today and tomorrow. So the ambition is to be with our processor in the 2 first exascale machine that will be installed in Europe, the one in Germany. So it's been announced that Jülich will host the first exascale machine in Europe. The second one will very likely be installed in France. So the RFP for the hosting entity will start in H2 this year, so maybe in September, October. So we should be in the 2 machines with the first generation of processor in the first machine, the second generation in the second machine. And what is very interesting is that we start working with ARM because it's a mature software ecosystem. It's a mature instruction set with almost all applications already ported on ARM. So with very high TRL, technical readiness level. And in parallel, we start developing RISC-V based technologies at the IP level in order we can mature the IP and the software ecosystem to be ready with high-end solutions by the end of the decade. So we don't believe that with RISC-V we can have supercomputers, I mean high-end supercomputers in production before 2028, 2030. So we move slowly. It's not, when I say we, it's not just SiPearl. This is the industry. The industry is moving slowly toward RISC-V but is moving to RISC-V. So we have anticipated with the European Processor Initiative, and we are combining on the same roadmap ARM and RISC-V. So this is what is described on this chart. The short term, we embed in the first generation of microprocessor that is described here, why not directly, some accelerator IP with a tensor accelerator, with a vector accelerator, with a stencil accelerator and an FPGA. And through time, through the generations, we will add more and more RISC-V compute IPs, including at some point of time, general purpose compute IPs. Yeah, and something very important as well, through time, we'll move to a single die. So what's inside what we call a socket. This is a package. Inside the package, today it's a single die, a single piece of silicon. So AMD did introduce a concept of multi-die, multi-chiplet. So all the industry is moving to this sort of assembly inside the package, because this is the only way to have a giant packages and giant processors. So we have designed the REA processor. REA is the code name and the commercial name of the first processor we are designing. REA is the mother of Zeus, because the core we are using, the Neoverse V1, its code name at ARM is Zeus. That's the rationale behind. So obviously there is no number on this slide because it's still under NDA. So I will be very happy to disclose more, but contact me and we'll sign an NDA and I will disclose. So it is based on the ARM instruction set, Neoverse V1. What is very interesting, I think that is very interesting for the developers and the end users, we use reasonably short vectors, 256-bit long vectors. So it means that in terms of application optimization, it's much easier to use 256 long bits than to use 5512 or 1024 bits long vector. If you have worked with a Knight series from Intel, it was a nightmare to optimize just because of the so long vectors. Even today, optimizing an application for AVX 512 is very complex. Most of the time, you cannot obtain the best of the peak performance just because of the long vector and the limited memory bandwidth that is associated with the long vectors. So you have a very poor, let's say, information flow per cycle toward the vector. So in terms of metric, this is the byte per flop ratio. How many bytes per floating point operation per cycle? So today, the metrics in the industry is about 0.1, meaning that just to get 1 byte, you need 10 cycles. It doesn't make sense. You have a fantastic core with long vectors that can work like hell with massive floating point operations, but you cannot feed it. So it's just something that doesn't make sense. So we try to solve this issue with shorter vectors and implementation of HBM on the die. So with massive memory bandwidth with HBM and reasonably limited vector length, meaning that we will really improve the byte per flop ratio, really improve, at least by a factor of 2 to 3 compared to Intel and AMD, and even compared to the best-in-class CPU, which is in a Fugaku machine, will be at least twice better. So we think that for most of the users, just using -03 optimization flag will be enough to obtain very good performances. Because the compiler has, I wouldn't say the compiler has nothing to do. It has very limited work to do. So the developer has very limited the job to do to obtain performances. As a consequence, the developer can spend more time on GPU optimization. So the less time you spend on CPU, the more you spend on GPUs. So it's better for everybody. So this is the real objective of the machine, of the CPU we are designing. So combined with HBM, we also have DDR. In order you can have all the services, let's say file system, Linux, and all of that in the slow memory, because it's just stupid to use HBM for running Linux, and you can dedicate the HBM memory for running. And I'm going to elaborate on that in terms of co-design. Top of that, we'll have lots of PCI Express lanes and CXL connections with PCI Express. In order, we can start combining the memory from the CPU and the memory of the GPU together in the same model. So it's not yet CXL type 2 that will unify the memory between the CPU and the GPU, but at least we are implementing type 1 and type 3, which is the memory on one side or the memory on the second side. So that will be an intermediate step that makes a lot of sense toward the future. For us, it's important to work with a CXL because it is a standard. We don't want to enter a proprietary approach like NVLink, like Hyperlink, because we believe that you as end users, you want to have the possibility to switch from one physical environment, one hardware to another one with no effort to report, to re-optimize, to recompile, to re-debug, and so on and so forth. So we want to avoid that. This is why we prefer to be maybe one step behind in terms of integration of technology, but just to work with standard technologies. It's very important. And all the cryptographic and security features are 100% designed in Europe by European people. So if we have a specific request coming from a government in terms of audit, in terms of backdoor control, we are on the safe side. That is also very important. When I say that we combine CPU and ARM and RISC-V, you can see here what I am talking about. So I prefer to explain in the later slides what I mean with STX and ERAC. You will see some concrete examples. And this is something that could be of interest for you to test. Everything about RISC-V is either control cores, something you don't see for the clock control, for the power monitoring control, and power capping control. So it's totally invisible. What is visible is the acceleration IP, acceleration block that we implement in the processor just to test. It's a unit acceleration block just to test the application. There's no way it can be put in production at a large scale. It's not designed for this purpose. This is for testing. So the first acceleration IP we are implementing is developed by the Fraunhofer Institute as part of the European Processor Initiative. This is a stencil. So I don't know whether the bioinformatics and the applications you use to work with make massive use or not of stencil, but this is designed for the most classical, let's say HPC and mathematical and numerical models. So everything that is explicit in time makes massive use of stencils. So this is an area where co-design makes a lot of sense. There are very little changes to do in the source code. It's mostly pragma to and then to recompile, obviously, to test this stencil. And from the very early comparisons with classical GPUs, and the one that has been compared is the Ampere A100 from NVIDIA, on the two oil and gas models, so it's not in your activity. It is for reverse time migration and reservoir simulation. In terms of mega stencil per second per watt. This is at least 3 to 9 times better than A100. So it's very, very promising. It's a very promising technology. So for stencil, it's very specialized, but it is designed for this purpose. And again, for this, HBM will make a big difference in terms of performance. Going to move fast. Something that is also very interesting with a strong potential is an IP for variable precision that is designed by CEA. And the goal is to minimize the effort in terms of precision. So instead of reducing the precision, you increase the precision dynamically on the fly in order, for instance, instead of using an inverse method or indirect method to solve a matrix, you can keep using direct methods. This is just perfect for the Hill conditioned matrices. So this is designed specifically for this need, and you can reduce the time to result by a factor of 10 to 50, depending on the matrix and depending on the specifics of your model. You can also reduce a lot the effort on the preconditioning phase for preparing your matrix. So this is something with a strong potential, but it has to be understood and analyzed in detail for each mathematical model on each domain to better understand whether it makes sense to use it or not. That is also something interesting for co-design. Another point for co-design is how to make a good use of the memory. I did mention we have HBM and DDR. It's not a unified memory. It's not HBM as a cache. It's in Linux, you will have two different memory spaces. One DDR, one HBM. So we have to work together, and this is something my team is ready to do, to support you, to take advantage of the two memory spaces. Maybe it's a bit more complex to use, but when it is done, when the job is done, it works. I'm very practical. I know that we already had this kind of technology in the past in the night landing series from Intel. But in the night landing, you also had the possibility in the BIOS to switch to HBM as a cache. All users said, oh, having separate memory is the best way to go. And all of them activated the HBM as a cache mode because it is much easier to use. So I know that this is not optimal for developers because they will have to spend some time to make the difference between the two memory spaces. And I know that for REA 2, that will contain HBM as a cache. They will forget this and move to HBM as a cache working mode. But anyway, I know that for the people making the effort to use it properly, that will be very, very efficient. So we will have a board that will be ready for testing, and this is designed with Atos. That will be ready for testing in say September next year, September, October next year. That will be a single socket or dual socket board with the different PCI Express and extension you can that you can see here. On the right-hand side, you can see the very, let's say, simple representation. On the left-hand side, you can see the detailed view on the different attachments you can have on the board. So it's quite flexible with a lot of different possibilities. Performances, something I used to show, and I will move very, very fast through this segment. So to make it short, when you want to maximize the flops, you go to GPUs. When you want to minimize, to maximize the memory bandwidth, you go to CPUs. On the x-axis, this is the peak in gigaflops or teraflops. On the y-axis, this is the byte per flop ratio. So you can see that the CPUs are more and more on the y-axis with very low gigaflops or low peak performance compared to GPU. So making any kind of comparison between CPU and GPU on peak performance and impact peak performance is just stupid. This is a game that CPUs just can lose. And the byte per flop ratio is associated to the HPCG benchmark, which is a solver using an indirect method, a conjugate gradient for matrix. And when you look at the efficiency per watt, you can see that when you combine ARM instruction set and HBM, not only you have great performances for HPCG, plus you've got much better performance per watt. And for most of the applications not fitting in GPUs, the matrix of choice is HPCG. So if you want to have the right combination of CPU and GPU for performance on performance per watt, the best you can do is to make the right choice for the GPU from this standpoint, and for the CPU to combine ARM on HBM, and you will have the most optimal approach. So here, this is mostly for you to read offline, just to say that one of the big advantages of ARM instruction set, it's a modern instruction set. So for the most usual operations, addition, multiplication, division, FMA, square, blah, 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 the number of cycles to perform the operation is reduced with ARM compared to x86. So it is one of the reasons why ARM is better than x86 in terms of performance per watt. Because for doing the same, you need less cycles. This is public information now. So you have the reference at the bottom of the slide. So you can see it represented differently, but all of that is really for your understanding. In terms of HPCG efficiency, so we think that with the REA processor, the green bar will be around more than 7% and close to 8% of the peak. The peak is the peak performance. So the ratio between HPCG and peak will be 8%, around 8% on REA, compared to what you can see with Genoa, A64FX, and SiPearl Rapid. So we are much more efficient on this standpoint. So on here, you can see the flops per gigahertz, which is also an important metric because gigahertz is also associated to performance and to power consumption. So from this standpoint, you can see on the A64FX and SiPearl Rapid the benefit of HBM, but they use long vectors, 512. While you can see an additional step of benefit with REA because of the SV256 vector length. So more or less the same. And that's it. I've been very short. I could spend hours on the performances, but I wanted just to show you that with REA, we don't focus on peak performance, definitively not. We focus on real efficiency for the real applications. And my key strategic focus is to deliver to the end users a processor that is very easy to use. You compile and boom, it works. This is all what I want. I want you to spend your time on GPUs and you don't waste 1 second on the CPU. This is my objective. That's it.
Thanks, Jean-Marc. So